Next speaker is Pankaj Saini from CMI. I hope Pankaj is around.
Yeah, can you see my slides?
Yeah, and we can hear you well also. So get started.
Okay. Okay, so first of all, I would like to thank the organizers for giving me the opportunity to talk. So in this talk, I'll be talking about the systematic biases on parameterized test of GR and due to neglect of orbital eccentricity, and how these systematic biases affect the parameterized tests of GR. And this work I've been doing with Mark Favata and KG Arun. So as you know that the Einstein's theory of gravity is the most accurate theory of gravity as of now. And there have been many tests performed on this theory with no deviations found till now. And you can see on the right plot, this plot shows the various regimes of gravity plot by different experiments. So the x-axis shows the gravitational potential, which is proportional to v by c square, and v is the characteristic velocity of the source. And the y-axis is the curvature scale. So all the solar system tests lie at the lower left corner of this plot, where the gravity is weak and the velocities are small. And the binary pulsar test lie in the middle of this plot. And whereas the gravitational wave observations lie at the top right corner of this plot, where the systems are highly relativistic and the gravity is strong. So these observations allow us to test Einstein's theory in the most violent region of space-time. This figure shows that three stages of dynamical evolution of binary black hole: the inspiral, merger, and ring down. So during inspiral, the binaries are far apart and the velocities are small. So this part can be described by the post-Newtonian theory, whereas the merger part requires numerical relativity simulations, and the ring down part is described by the black hole perturbation theory. So during inspiral, when the velocities are small, we can expand the orbital phase in terms of the orbital velocity, and so this is given as a series in powers of v by c, and these coefficients, the phi's, are called the post-Newtonian coefficients. So this phi naught is the lowest order GR term, and then there are higher order corrections to it, and this is the negative PN term. This is the dipole term, which is 0 in GR but non-zero in some alternative theories of gravity. So if you see that this is the negative powers of v, so this term dominates at the lower frequency or the lower orbital velocities, whereas the other higher order PN terms dominates at the higher frequencies. So in GR, given the masses and spins of the source, the value of these post-Newtonian coefficients have a unique value, and if there are additional fields in the vicinity of the binary black holes, the energy and angular momentum may be transferred to these additional fields, and this change in the energy and angular momentum may be reflected as a deviation in the gravitational wave phase. So to account for these kinds of deviations, we use parameterized test. So in parameterized test, we introduce these non-GR deviations as a free parameter. So these delta phi hat are the deviation coefficients which are introduced as free parameters, and these free parameters captures the deviation from GR, and the value of these deviation coefficient is constrained by the data. So if GR is the correct theory of gravity, then the value of these deviation coefficients should be consistent with 0. And also so in alternative theories of gravity, these deviation coefficients assume some specific values. And so if you can constrain these deviation coefficients, then you can constrain the parameter space allowed by some alternative theories of gravity, and maybe rule out some of the alternative theories of gravity. So these are the bounds on these deviation coefficients using the third gravitational wave catalog. On the left, we have the dipole term, and on the right, we have the positive post-Newtonian coefficients. So these horizontal bars represents the bounds obtained using the individual event, and with a color coding representing the chirp mass of the system in the detector frame. And so the general trend is that the lower mass systems constraining these parameters better compared to the heavier mass ones. And these blue diamonds are the combined bounds from these individual events. And the dipole term is the most tightly constrained term, and whereas this leading order deformations have around 10 to the power minus 1, And as we go to the higher post-Newtonian orders, the bounds become weaker. So in driving these bounds, it was assumed that by the time the binary enters the frequency band of these detectors, the binary becomes circular. And there is a good reason to believe that, because eccentricity is a sharply decreasing function of frequency. So as I said, the gravitational wave extracts the binding energy and angular momentum from the system, and the loss of binding energy tends to shrink the orbit of the binary. And whereas the loss of angular momentum tends to circularize the orbit. So this circularization is very effective, as you can see from this figure. So if you start with a very high eccentric binary, suppose the eccentricity is 0.9, and when the binary was emitting at 10 to the power minus 2 hertz, so by the time the binary enters the frequency band of this detector, which starts around 10 hertz, the binary almost becomes circular by shedding away all its eccentricity. So in the absence of fast and accurate eccentric waveform models, we use quasi-circular waveforms for parameter estimation of these eccentric binaries. But there are scenarios where binaries can have highly eccentric, the binaries can be highly eccentric. So in globular clusters and the nuclear star clusters, where the density of the stars is very high, and due to various interactions among these objects, the highly eccentric binaries can be produced. And there have been various studies on this topic. So, and which claim that a good fraction of these binaries will have non-negligible eccentricity when they enter the frequency band of these detectors. And if we use a quasi-circular waveforms for doing the parameter estimation for these highly eccentric binaries, and this will introduce the systematic errors in the estimated parameters and the deviation coefficients. And the systematic bias on these deviation coefficients may mimic the deviations from GR, and which will lead us to falsely claim a deviation from GR. So just to give an overview of systematic biases, so these biases are due to our imperfect model that we use in our data analysis. And so this systematic biases basically shifts the mean of the distribution from the true value. And these are defined as the difference between the true value of the parameter and the best fit value of the parameter, which maximizes the likelihood in the data. So suppose we have an approximate waveform, which is described by the approximate amplitude and the approximate phase. And this is the best waveform model available to us. And the true waveform is different from this approximate waveform by amount delta A in the amplitude and this delta psi in the phase. And these are the corrections due to the eccentricity in the amplitude and the phase. So we can calculate the systematic errors by using the Cutler-Evaluationary formalism by using equation 6. And so this is given by this inner product between these two quantities. And the sigma AB is the covariance matrix, which is calculated using the approximate waveform. So we use Taylor F2 eccentric waveform model, which describes the spiral part of the waveform. And the phase of this waveform model can be decomposed into two parts, the circular and the eccentric part. And the structure of the eccentric part can be seen from this expression. This is expanded in powers of V and V naught, where V naught is defined as pi m F naught, and where F naught is the reference frequency where we define our initial eccentricity E naught. And this waveform is valid for small eccentricities less than 0.2. So we use Fisher information matrix to get the bounds on these deviation coefficients, which gives the 1 sigma width of 1 sigma width of the distribution around these parameters. And our parameter set consists of the following parameters. Tc, phi, c are the time and phase of coalescence, and m and eta are the mass and mass ratio. And chi1, chi2 are the spins of the two black holes, and this delta phi hat k's are one of the deviation coefficient. So we only vary one of the deviation coefficient along with other GR parameters at one time, because we are limited by the sensitivity of our detectors. And if we try to simultaneously vary all the deviation coefficients at one time, then it will lead to an uninformative bounce on these deviation coefficients due to various correlations and degeneracies present among different parameters and the deviation coefficients. So all our sources are fixed at a distance of 500 megaparsec, and the mass ratio is set to be 1:2. and initial eccentricity is defined at a reference frequency of 10 Hertz. So we want to quantify the effect of orbital eccentricity on these deviation coefficients by comparing the systematic biases and the statistical errors.
Yeah, 2 minutes to go, Pankaj.
Okay. So we see that at water centricity, these systematic errors becomes comparable to the statistical errors. So in these plots, we saw these systematic errors and the statistical errors on the leading order on the leading order deformation coefficient. And the systematic errors are denoted by the solid lines and the statistical errors are by the dashed lines. So if you see that as the eccentricity increases, the systematic errors also increases and becomes comparable to the statistical errors with the intersection point depending on the mass of the system, with the lower mass systems crossing the statistical errors at first, because the lower mass systems have longer in spiral in the band, so they have large number of gravitational wave cycles in the band, and systematic errors is a cumulative effect which accumulates over many gravitational wave cycles. So that's why the lower mass systems crosses the statistical errors at first. And the right plot shows these errors on the cosmic explorer band, which has better sensitivity compared to advanced LIGO, and especially at low frequencies. So if you see that the systematic errors crossing the statistical errors at an eccentricity of around 5 into 10 to the power minus 3. So if a source, even with a very small eccentricity, is observed in this C band, then the systematic errors will become comparable to the statistical errors. And this value was around 4 into 10 to the power minus 2 in the advanced LIGO band. So for all the deviation coefficients in advanced LIGO, so all the deviation coefficients are affected differently if in advanced LIGO, and especially the lower mass systems crossing the statistical errors first. And similarly for the C, we have means the systematic errors starts dominating even at very low eccentricities. So this will be a more serious issue for 3G detectors, right? So just to conclude that a fraction of binary black holes may have non-negligible eccentricity while they are observed in the ground-based detectors, depending on the formation history. And the use of circular waveforms will introduce the systematic biases in these deviation coefficients. And for advanced LIGO, this eccentricity is around 4 into 10 to the power minus 2. And for C, the eccentricity is around 5 into 10 to the power minus 3. So these eccentricity-induced systematic biases will mimic the deviations from GR. And so to control the systematic biases due to eccentricity will be of great importance for the third generation detectors. Yeah, so thanks for your attention.
Okay, great. So we have a few minutes for the questions. Any questions to Pankaj?
Yes, can you go to slide 5?
Yeah.
So you said that the significant fraction may have, the significant eccentricity for which systematic bias may be comparable to the statistical. So what is that fraction? So how much?
Yeah, so if you go to
number,
yeah, so if you go to these references, suppose this reference, so they perform n-body simulations on these globular clusters and the nuclear star clusters. So they found that using n-body simulations, around 20% of these binary black holes which are merging inside these globular clusters will have a non-negligible eccentricity while entering these ground-based detectors. So this fraction varies from paper to paper actually. So it starts from 5% to 20% and so on.
yeah. So this significant fraction and having what some approximate eccentricity they have given, or
yeah, so they found that so
is
yeah,
it 10
so,
to the power minus 2 or 10 to the power minus 3 or
yes,
something? But
so it is around 0.1. So this 20% fraction is greater than 0.1 eccentricity. Yeah.
Okay.
One more thing.
Any-
Okay, can you go? Okay.
Yeah. No, go
Yes,
ahead.
slide. Can you go to slide 9? When we go from echo to C, so there are two things. So we have slightly more in spiral because it is starting at 5 hertz. So, and also sensitivity is more. So have you checked whether this improvement, I mean, this systematic bias is getting comparable to statistical at smaller values of eccentricity? So the effect is due to the sensitivity or due to slightly more in spiral. So which effect is more? Have you checked that?
We have not checked that explicitly, but I assume that this is due to the large number of gravitational wave cycles spent in the band, because the systematic biases are proportional to the number of cycles spent in the frequency band of the detector. So that should be that. Yeah.
Okay.
Okay, Pankaj, maybe last question from Aditya is about to quantify the SNR dependence of your result. I guess the systematic bias does it depend upon the SNR or not? Maybe with that we can conclude if you answer.
Okay, so yeah, if you go to this expression, so this equation 6 describes the systematic errors. So the sigma AB is the covariance matrix. This covariance matrix goes as 1 by SNR square, and this inner product on the right hand side, it is proportional to the SNR square. So this cancels out this factor. So these systematic errors are independent of this SNR. Yeah.
Okay, thanks, Pankaj. So I think with that, I think thank you so much. Thank you so much to all the speakers who spoke on their results and so on. So I think back to you, Sridham, if you want to make any announcement.
Yeah, thank you, Arun, for chairing this session, and thanks to all the speakers.